Floating in the hostile waters of Norway's Fjordhavet region is a structure that defies standard agricultural logic. It stands 68 meters tall, roughly the height of a 22-story building, and weighs a crushing 7,700 tons of solid steel. To the untrained eye, this looks exactly like a semi-submersible oil rig designed to drill deep into the Earth's crust. But below the waterline, this machine is not extracting a single drop of fossil fuel. Instead, it is holding a massive biological payload, 1.5 million Atlantic salmon. This presents an immediate financial and logical paradox. Why would Salmon, a commercial entity, invest an estimated $300 million to move their food production into one of the most volatile environments on Earth? This is a maritime zone where wave heights regularly exceed 10 meters, hydraulic force enough to shred traditional plastic fishing cages in a matter of minutes. The reason for this extreme engineering is not ambition. It is desperation driven by two critical factors. First is the biological enemy. Traditional aquaculture in Norway's sheltered fjords is facing a crisis caused by Lepiophtheris salmonis, the sea louse. In the shallow, slow-moving waters near the coast, these parasites proliferate uncontrollably. They attach to the salmon, consuming their skin and blood. This infestation forces the industry to spend billions of dollars annually on chemical treatments and mechanical delousing, which stresses the fish and destroys profit margins. Second is the physical limit. The coastline is simply full, with millions of fish concentrated in static waters. Biological waste and uneaten feed settle on the shallow seabed, creating localized pollution zones. The biological carrying capacity of the fjords has been reached. To save the industry, farmers had to move into the open ocean, where strong currents naturally disperse waste and disrupt parasite cycles. However, standard plastic equipment cannot survive the physics of the high seas. To solve a biological problem, Norway had to abandon farming tools entirely and adopt the heavy-duty engineering standards of the offshore oil and gas industry. To turn this blueprint into reality, Norway had to look halfway across the world. While the engineering schematics were drawn in Scandinavia, the physical construction took place at the Wuchang Shipbuilding Industry Group in China. This decision was driven by the sheer scale of the material requirements. The project demanded 7,700 tons of steel. That is roughly the equivalent of melting down the entire Eiffel Tower and forging it into a single aquatic structure. Once completed, the logistics of delivery were equally monumental. The rig could not move under its own power. It had to be lifted onto the deck of the Xian Guanghua, one of the world's largest semi-submersible heavy lift vessels, with a deck the size of 3 soccer fields. This convoy traversed over 15,000 miles from the East China Sea to the North Atlantic. The payload was so wide, spanning 110 meters, that it physically eclipsed the wingspan of a Boeing 747, requiring precise navigation to avoid capsizing during the 49-day journey. But the real engineering magic happens once it is in the water. How does it survive a North Atlantic storm with 10-meter waves? Forces that would snap a traditional plastic cage like a twig. The secret lies in the ballast system, a technology borrowed directly from nuclear submarines. The rig stands on giant hollow steel legs. When meteorological sensors detect a pressure drop indicating a storm, the crew does not panic. Instead, they activate high-capacity pumps to flood these legs with thousands of tons of seawater. This extra weight anchors the rig, physically sinking its draft from 16 meters down to 25 meters. Instead of bobbing around on the surface like a plastic cork, the structure becomes a heavy, immovable steel island. The lattice design allows the wave energy to pass through the structure rather than smashing against it, keeping the water inside the cage relatively calm even while a hurricane rages outside. Inside this fortress, there is another piece of brilliant mechanical design, the movable bulkhead. In traditional farming, catching fish is chaotic and dangerous, often requiring divers to enter the water. Ocean Farm 1 solved this by turning the bottom of the cage into a giant hydraulic elevator. The floor is not fixed, it sits on guide rails. When it is time to harvest, the crew simply pushes a button. The entire floor, a surface area of 28,000 square meters, slowly rises. It acts like a massive piston, gently pushing all 1.5 million fish up to the surface. It allows the crew to inspect or harvest the salmon without a single human ever getting wet. Controlling this 68-meter-tall mechanical beast requires shockingly few people. The entire facility is run by a skeleton crew of just 3 to 7 engineers. A naval vessel of this size would typically require a crew of 50. How do they do it? They don't guess. The rig has a nervous system of 20,000 sensors capturing over 1.5 million data points per day. These sensors track everything from oxygen saturation to current velocity, allowing the small crew to play a video game of resource management while the machine does the hard labor. Once the structural integrity is verified by the sensor network, the facility transitions from a maritime engineering project to a biological production site. The life cycle inside Ocean Farm 1 is a strictly controlled industrial process designed to optimize growth rates while mitigating the specific biological risks of the open ocean. Stage 1. The injection of biomass. The fish do not hatch here. The volatile conditions of the North Atlantic are too harsh for eggs or fry. The production cycle begins on land-based hatcheries, where Atlantic salmon are raised in freshwater tanks until they reach the smolt stage, weighing between 250 to 400 grams. At this specific weight, the salmon undergo physiological changes, smoltification, that allow their gills and kidneys to process saltwater. Transporting 1.5 million living creatures from land to the offshore rig requires military-grade logistics. Salmar utilizes specialized wellboats, vessels equipped with massive internal water tanks. Upon arrival at the rig, the fish are not netted or hoisted, which would damage their protective mucus layer and scales. Instead, they are transferred via a high-volume, low-pressure hydraulic pumping system. Large diameter hoses connect the ship to the rig, and the fish are injected directly into the 250,000 cubic meter enclosure. This wet transfer ensures that from the moment they leave the hatchery to the moment they enter the ocean, the fish never leave the water. Stage 2. The subsea feeding strategy, lice avoidance. Once the biomass is established, the primary operational challenge is feeding. In a traditional farm, pellets are scattered on the surface. However, Ocean Farm 1 employs a subsea feeding strategy, driven by pneumatic mechanic. The sea louse, or Lepiopterus salmonis, is phototactic, meaning it is attracted to light and congregates in the upper water column, specifically the top 0 to 5 meters, to physically separate the host, salmon, from the parasite, lice. The rig's feeding system bypasses this danger zone entirely. The central silo mixes feed pellets with water and uses compressed air to fire this mixture through submerged pipes, ejecting the food at a depth of 8 to 10 meters. Because salmon are conditioned to follow the feed, the entire school of 1.5 million fish is forced to swim and feed in the deep zone, well below the surface layer where the lice swarm. This creates a natural depth shield. By manipulating the vertical position of the fish using food as a lure, the facility dramatically reduces infestation rates without the need for chemical pesticides. Stage 3. Automated hydrodynamic maintenance. Maintaining the cage environment is critical for oxygenation. The net of Ocean Farm 1 spans a surface area of 28,000 square meters. In the nutrient-rich ocean, biofouling, algae and mussels can clog the mesh within weeks. Blocked nets reduce water exchange, causing oxygen levels inside the cage to drop, which stunts fish growth. Traditional farms use copper-based anti-fouling paint to kill algae, but copper is a heavy metal that leaches into the marine ecosystem. Ocean Farm 1 eliminates this toxicity by deploying a fleet of autonomous cleaning robots. These underwater drones are equipped with magnetic wheels or thrusters that lock onto the net. They traverse the vertical walls of the cage 24 hours a day, using rotating high-pressure water discs to blast away organic buildup. This mechanical cleaning ensures that the hydrodynamic permeability of the net remains near 100%, allowing the ocean currents to flush the cage with fresh, oxygenated water constantly. Stage 4. The precision harvest. The grow-out phase lasts for 12 to 14 months. During this time, the salmon grow from 400 grams to a harvest target of 5 to 6 kilograms. When the sensors indicate the biomass has reached optimal weight, the harvest sequence is initiated. This is where the movable bulkhead proves its value. The hydraulic floor slowly rises, reducing the volume of the cage and gently crowding the fish toward the surface. Unlike net fishing, which causes panic and physical damage, this method controls the density precisely. A processing vessel docks alongside the rig. Large intake tubes are lowered, and the salmon are live pumped from the ocean into the ship's hold. Immediately upon entering the vessel, the fish pass through a rapid cooling system, superchilling. The water temperature is dropped to near freezing. This induces immediate sedation, hypothermia, rendering the fish unconscious before they can experience stress. This detail is chemically important. Stress causes fish to release lactic acid into their muscle tissue, which degrades the meat texture and turns it soft. By stunning the fish instantly with cold water, the muscle pH remains neutral. The fish are processed, bled, and gutted within minutes on the vessel, preserving the firm structure of the meat before it is transported to the mainland. The entire cycle, from the ocean to the factory box, is a closed loop of industrial precision. The culmination of this engineering feat is a production volume that rivals industrial manufacturing. A single operational cycle at Ocean Farm 1 yields approximately 10,000 tons of processed salmon. To visualize this mass, imagine a convoy of 500 heavy-duty semi-trucks, bumper to bumper, fully loaded with fish. In nutritional terms, this single structure generates enough protein to serve 10 million dinner plates, effectively feeding a population the size of Sweden from one location. But the most critical metric for the engineers is not total volume. It is the feed conversion ratio, known as FCR, which measures biological efficiency. While cattle require roughly 7 kilograms of feed to produce a single kilogram of beef, and pigs require about 3 kilograms, Ocean Farm 1 achieves a ratio of approximately 1.05. This near 1-to-1 ratio means the system is thermodynamically optimized, converting almost every gram of protein input directly into muscle mass, making this the most efficient animal protein production machine on the planet. The quality of this biomass is also fundamentally distinct from traditional aquaculture. Because the rig is positioned in high-energy waters with currents consistently moving at nearly 1 meter per second, the salmon are forced to swim constantly against the flow to maintain their position. They are living in a perpetual current gym. Post-harvest analysis confirms that this physical exertion results in a firmer muscle texture and a lower fat percentage. The meat possesses a structural integrity that bridges the gap between the soft texture of fjord-farmed fish and the lean muscularity of wild-caught salmon. Financially, the high-tech gamble pays off. With the global market price for premium Atlantic salmon oscillating between $7 and $9 per kilogram, a single harvest generates a gross revenue estimated between $70 million and $90 million. While the initial capital expenditure of $300 million to build the rig was astronomical, the operational expenditure is incredibly low. Because the facility is fully automated and requires only a skeleton crew of 7 people, the labor cost per kilogram of fish is a fraction of traditional methods. The final product is not destined for cans or frozen fish sticks. Due to its superior texture and its status as an eco-friendly product, this salmon is exported globally. It is flown fresh to high-end markets in the United States, Europe, and Asia, specifically targeting the sushi and sashimi sectors, where the firmness of the meat and the story of sustainable, chemical-free offshore farming command a premium price. However, the transition from traditional farming to heavy engineering is not without peril. Relying on complex machinery in the corrosive environment of the open ocean introduces a new category of risk. In September 2018, shortly after its deployment, Ocean Farm 1 experienced a critical stability incident. A malfunction in a compressed air valve within the ballast system caused the massive structure to tilt dangerously in the water. While the automated safety protocols eventually corrected the list and prevented a structural collapse, it served as a stark warning. When a passive net is replaced by an active machine, mechanical failure becomes a possibility. In the unforgiving conditions of the North Atlantic, a stuck valve or a software glitch is not merely an operational inconvenience. It is a potential maritime disaster. Beyond the physical risks, there is a profound economic barrier. The capital expenditure required to build a single unit ranges from $100 million to $300 million. This price tag fundamentally alters the demographics of the industry. It effectively eliminates the independent farmer from the equation. Only sovereign wealth funds and multinational conglomerates possess the liquidity to finance these steel islands. This signals a permanent shift where global food security becomes the exclusive domain of corporate titans rather than local coastal communities. Despite these hurdles, the model is being aggressively replicated. The blueprint established by Ocean Farm 1 has triggered a global race to colonize the high seas. China has already launched Deep Blue 1, a similar submersible cage operating in the Yellow Sea. Meanwhile, the United States is currently reviewing federal regulations to open its exclusive economic zone to heavy industry aquaculture. The era of hunting for fish is ending. The era of manufacturing them at sea has begun. Ocean Farm 1 demonstrates that humanity possesses the technology to feed the planet without exhausting our remaining arable land. But it forces a difficult question. Is the industrialization of our wild oceans the only path forward? If you found this engineering analysis valuable, please hit the like button and subscribe to the channel for more deep dives into extreme agriculture. I want to hear your perspective in the comments below. Do you trust high-tech fish grown in a robotic rig more than fish caught in the wild? Thank you for watching.